What specific problem or gap in mechanistic interpretability does the switch sparse autoencoder address, particularly in relation to existing sparse autoencoder methods?
The switch sparse autoencoder, switch say, addresses the dual bottlenecks of memory and computational complexity, flops, that existing sparse autoencoder methods face, particularly during the training of large language models. Traditional sparse autoencoders, such as top-K SAEs, struggle with the dense encoder forward pass, which limits their scalability as model sizes increase. By introducing a routing network that activates only a subset of expert SAEs based on the input, the switch say effectively reduces the number of flops per activation while maintaining or improving reconstruction performance. This conditional computation approach allows for a more efficient use of parameters and memory, enabling the training of larger models without a proportional increase in computational cost. Thus, the switch say not only enhances the interpretability of model features, but also optimizes the training process, filling a critical gap in mechanistic interpretability.
Can you explain in detail how the switch sparse autoencoder works? Please illustrate the main steps of the algorithm, including the role of the routing network and expert SAEs.
The switch sparse autoencoder, switch say, operates by utilizing a combination of multiple expert sparse autoencoders and a routing network to optimize the processing of input data. The architecture consists of n expert SAEs, each resembling a top-K say, and a routing network that determines which expert will handle a given input. The routing network computes a probability distribution over the experts using a softmax function, allowing it to select the most suitable expert based on the input's characteristics. During the forward pass, the input is routed to the selected expert, which processes the input and generates the output reconstruction. The training of the switch say involves simultaneously optimizing both the router and the expert SAEs. The total loss function combines the reconstruction loss, which measures the difference between the input and its reconstruction, and an auxiliary loss that encourages uniform routing across the experts to prevent overloading any single expert. This design allows the switch say to effectively manage computational resources while maintaining high reconstruction fidelity, as it can reduce the number of flops per activation significantly compared to traditional methods. Overall, the switch say architecture enhances efficiency by leveraging conditional computation, allowing for a scalable approach to training sparse autoencoders.
Provide a simple example that demonstrates how the routing network selects an expert say, and how the input is processed through this selected expert in a practical scenario.
In a practical scenario, consider an input activation vector, x, that needs to be processed by the switch sparse autoencoder, switch say. The routing network first computes a probability distribution, px, over the n expert SAEs using the formula px equals text softmax w underscore text router xb underscore text router / closing parenthesis dot. This distribution indicates the likelihood of each expert being the most suitable for the input. The expert with the highest probability, denoted as x equals underset I text argmax p underscore I x, is selected to process the input. Once the expert x is chosen, the input x is routed to this expert, which then outputs a reconstruction x based on its learned features. This process allows the switch say to efficiently utilize its resources by activating only one expert at a time, thereby reducing computational costs while maintaining performance.
In terms of performance, what theoretical or practical advantages does the switch sparse autoencoder offer compared to traditional sparse autoencoders like top-K SAEs?
The switch sparse autoencoder, switch say, offers several performance advantages over traditional sparse autoencoders like top-K SAEs. Firstly, it achieves a lower mean squared error (MSE) for reconstruction while maintaining the same computational costs, demonstrating improved efficiency in training, page 6. Additionally, the switch say can reduce the number of floating point operations, flops, per activation by up to 128 times, which is particularly beneficial for larger language models, page 7. The architecture's use of conditional computation allows it to activate only a subset of expert SAEs for each input, which helps in managing memory and computational bottlenecks effectively, page 2. Furthermore, the switch SAE maintains comparable interpretability to top K SAEs, ensuring that the quality of feature representation is preserved, page 8. Overall, these advantages position the switch SAE as a more scalable and efficient alternative to traditional sparse autoencoders.
How was the effectiveness of the switch sparse autoencoder validated in your experiments? Describe the datasets, performance metrics, and comparative baselines used in testing.
The effectiveness of the switch sparse autoencoder, switch SAE, was validated through experiments using the residual stream activations of the GPT-2 small model, specifically from layer 8, which has a dimension of 768. The training involved approximately 820 million tokens from the OpenWebText dataset over 100K steps, with a batch size of 8,192. Performance metrics included reconstruction mean squared error, MSE, and the proportion of cross-entropy loss recovered when the sparse autoencoder output was integrated back into the language model. The switch SAE was benchmarked against several comparative baselines, including top K, gated and ReLU sparse autoencoders under both flop-matched and width-matched settings. Results indicated that switch SAEs achieved a Pareto improvement over the baselines in terms of MSE and loss recovered, particularly excelling in the flop-matched experiments while maintaining computational and memory costs.
What specific results did you obtain from the experiments with the switch sparse autoencoder, particularly in terms of reconstruction error and efficiency compared to other methods?
The experiments with the switch sparse autoencoder, switch SAE, demonstrated that it achieves a Pareto improvement over top K, gated, and ReLU sparse autoencoders in terms of reconstruction mean squared error, MSE, and loss recovered when trained under flop-match conditions. Specifically, as the number of experts in the switch SAE increases, performance continues to improve while maintaining constant computational and memory costs. In width-matched experiments, although switch SAEs underperformed compared to top K SAEs in MSE and loss recovered, they still outperformed gated and ReLU SAEs. Notably, switch SAEs can reduce the number of flops per activation by up to 128 times, while retaining performance comparable to ReLU SAEs. Overall, the results indicate that switch SAEs provide significant computational efficiency while preserving reconstruction quality, particularly in scenarios with a higher number of experts.